So we saw in concurrent invariants last time, and we saw some simple examples. But as I mentioned last time, the concurrent invariants, like, they are the heart of concurrency proofs, and they can get quite complicated. So we'll see a more complicated example with the we'll see many variants of the SPSCQ proof. We'll also do multiple producer, multiple consumer, and see how the specs change. And then we'll also see a new concept called monoids. I'll motivate why we need them. So let's look at SPSCQ. So this is like a circular queue. And there is only one, at any time, there is only one producer and one consumer, but they can race. So some animation. So at the beginning, when we start the queue, the tail and head are at the 0 element. And this is an array of size 8. And when we push something in the queue, the tail moves. So we have produced 11, then we have produced 22. And then when we consume from the head and move the head. So now the queue is empty again. So let's take an arbitrary state where we have produced a bunch of items, and the tail is where the next item would go, and the head is from where we'll consume. And one thing to note is that in this case, like in this design, the capacity is only 7. When at this state we stop. If we consider the queue full now, because if we push a new element, then we won't be able to figure out whether the queue is empty or not. So this was the state when the tail and head are the same, then the queue is empty. And when incrementing the tail, when that becomes the head, then we consider the queue full. So the main question is, we have to design the invariant for this, because both the producer and consumer, they are accessing the cells of the array, and also the head and tail are atomic counters. So let me show you the code. So the head and tail are two atomic counters, and we'll see the code of push in the animation anyway. Okay, so yeah, on the code, one thing I also wanted to show you is that the head and tail are atomic, but the buffer itself is non-atomic. Okay, so we have to design the invariant, and so the cells. One thing to note is that both the producer and so the consumer reads these cells and the producer writes to these cells. So there is a race between them. So one thing, so neither of them can like have exclusive ownership of these cells. So we have to put them in the invariant. If you go by the previous design. So one question is, what is the ownership that always lives? Which the ownership of which cells always live in the invariant? So one design is that the ownership of all the cells live in the invariant except the head and the tail. The head element, the ownership of the head element could have been removed by the consumer during the consume function, and the ownership of the tail element would be temporarily removed from the invariant during the produce function. So if you look at, this is the produce function, this is the body of the produce function. The first thing it does is loads the head. So the producer has the authoritative full ownership of the tail this tail counter. So only the producer changes the tail. So the consumer can read it. The consumer has like fragmentary ownership of the tail counter. The consumer can read it, but only the producer can change the tail. So the producer knows what the tail is. So the only thing that the producer doesn't know is like the head. So the producer, when it loads the head, at least in the logic, we know whether the queue is full or not. If the producer knows the tail, now the producer, after loading the head, the producer would also get to know the head. And the producer can decide at that time whether the operation will succeed or not, like which depends on whether the queue is full or not. So if the producer determines that the operation would succeed, then what the producer does is it removes the ownership of the tail cell from the invariant. Just we have to design the invariant in such a way that if the queue is not full at head.load, so at head.load, we will open the invariants, we'll open this invariant. We have to permanently take out this ownership of the cell, of this cell from the invariant, because we'll be writing to it. So we'll be writing to the tail in this step. So and that's not an atomic operation. It's not, yeah, as I mentioned, like this buffer, the cells are not atomic. So we have to like permanently take out. By permanently, I mean that even after closing the invariant, the ownership of this cell should fall out of the invariant. So when you close the invariant, you should not be required to put this cell back into the invariant. And all the other constraint is like when the producer starts, it must know that the ownership of this cell is in the invariant, and at the end of the load operation, it must be able to take out the ownership of this cell from the invariant. This is similar to the lock invariant we saw. So remember, we saw the lock invariant last time, where we said that this meeting is being recorded. Like, how can I remove that pop-up? It doesn't even show on my computer.
It's not sure, yeah.
It doesn't show you on. It doesn't show on your screen.
No, no.
Okay, good. Oh, so it's just on the TV. There is this. The atomic R bool. There is a missing here. It should say locked. So if you recall, what we did last time was this was the lock invariant here, and okay, thanks. Yeah, and so this was the key thing there was when the locked atomic goes from false to true, that's when the lock function returned. And so what that meant was before the lock operation succeeds, at that atomic operation, when the lock succeeds, when we open the invariant, we are guaranteed to find this thing. And when we close the invariant, the lock value is true. So locked value is true. So we are in this case. So we do not have to return this to the invariant. So we get to take it out permanently from the invariant. So we have to do a similar design here, where the content of the invariant is conditional, and some condition changes which allows us to take out this cell from the invariant. And then eventually we will write to that element. And because we took out the full ownership from the invariant, we can write to it. And once we write to it, and then we have to also design is in a way that when we do the store, this is the last atomic operation in the invariant. So when we open the invariant, and then when we close the invariant, we must be able to put this cell back into the invariant so that the consumer can read it. So these are some constraints in the design. So to understand the invariant, it may be useful to have some terminologies. So one I use two terms, num produced and num consumed. So num produced is the total number of elements that have been produced so far. And one thing to note is tail is always equal to the num produced mod 8. So every time we produce, we increment num produced, and the tail also increments and wraps around in the mod 8 integer field. And similarly, num consumed is equal to mod 8 is the head. So these equations would be useful. And so there are some other constraints. These are the two we talked about. If the num produced is equal to num consumed, then the queue is empty. So it means that we have consumed everything that we produced so far. It's full if num produced is 7 plus num consumed. We saw that the capacity was only 7, not 8. And there are some constraints like num consumed will always be less than equal to num produced and less than num consumed plus 7. With all these constraints we have to encode in the invariant, and the constraints would become slightly more complicated, but this is the rough idea, and I'll show you the exact value. So one thing to note, the final thing to note is, as I mentioned, we will do logical locations today, and one difference to note is that in the lock example, there was this field locked, which stored the value, which stored a Boolean, and when the value of that changed, we were able to pin whether or not lock protected resource is in the invariant. We were able to tie it to this locked variable. Like if locked is true, then we don't have anything. If locked is false, then we have that resource in the invariant. Again, this should be here. We should say locked. That the field locked has this value, cock value locked. But here we do not have anything to tie it to so head.load, it just reads the location, it just reads the value of the load. It doesn't change anything. So there is no physical thing that changes at this step. So we cannot tie whether this tail location is in the invariant or not. We cannot tie it to any like physical state. We can maybe tie it to like the program counter, like if the program counter goes from here to here, then we take out, but like the program counter itself is not something that we have access to in the logic, and for good reasons. Like we do not want we want the reasoning to be a somewhat high level, not dependent on exact details of the program. So one solution is like, the typical solution is like, just like we have these physical locations, like in the lock, we had a physical location which stored a Boolean. We can have logical locations where we can store any cock value, almost any cock value. There are some circularity issues, but in practice, we can store almost any value we usually care about. So we'll use that feature. So we'll have some logical location which stores whether the tail cell has been taken out of the invariant. And one precondition of push is that the tail value is there. And it also at the end, it must be there. But during the proof, we get in the proof, we get to change that logical location. So here we'll change that logical location to take out that cell. One final thing is, before we look at the code, is that just like in a lock, when we unlock, we give up this resource. We put this resource in the lock invariant, so that when somebody calls lock, it can take this back. So lock is a way to transfer some resource from the caller of unlock to the caller of lock. So this resource gets transferred from unlock to lock. Similarly, what we can do here is in many applications, we would like the flexibility of using this class to transfer resources from the producer to consumer. So what we can say is we will define an invariant in a way such that the client, whoever is using the class and the proof, they can come up with some P which defines the resource for the consumer. And whenever they call produce, they have to give up this P of that value. And when somebody calls consume, they get back P of the pop value. And this can be useful. So one example of P could be like the values in the queue could be indices of some other array. Like they could be in some networking library, there could be a packet array, and the values in this queue could be indices of that array. And in that case, P could be like the ownership of that cell. So when we push 33, we also transfer the ownership of the 33 number cell of that packet array into this class. And so that when the consumer calls consume, they get to take out not just the ownership of the cell, but also this P of 33 out of the invariant. That's it. So any questions? Now we look at the code. So this is the invariant. It looks quite large. Okay, so some things to note. So the P that I mentioned in the slide that's here, it's parameterized by the P. This is the ownership that the producer passes from, that is transferred from the producer to the consumer. So a few things to note is like the field head says that the field head has the value num consumed mod buff size, which is exactly what I showed in the slide. In the tail, and the tail is num produced mod buff size. So these two things we already saw in the slide. Uh, and then so we have this notation called logical R. So a queue is parameterized by a bunch of logical locations. So we have the invariant ID as before, and we also have the logical locations where we store a bunch of things. So these two logical locations, this one I motivate. So in produce log, this is the logical, this is the, this logical location stores a Boolean. It indicates whether we are in a produce, and if we are in produce, we have taken out the ownership of the tail cell already. So the way we assert that is we say there is some Boolean in produce that is stored at this logical location in consume in there is in produce location, in produce log has this Boolean in produce. So just like previously we in the log we could store a Boolean in a physical location. In the log class we stored a Boolean in a physical location. Now we are storing this Boolean in a logical location to track whether we have taken out the ownership of the tail cell from the invariant. So now we can use these two to constrain what is in the invariant. So it has a bunch of things. So at the end, it has the ownership of all the cells. So it has the ownership of the active cells, which store some element, and the ownership of inactive cells, which has like NER, which means that it could also be uninitialized in the beginning. And the active cells have some element. So if you look at active cells, in the beginning, so just for the beginning, we can just think of this as num consumed. Ignore num consumed also. This is just think of it for a minute. Just think of it as num consumed. So this is saying that starting from num consumed index, we are laying out all the elements of that are currently there in the queue. So the first element would be at num consumed, and the second element would be at num consumed plus 1, then num consumed plus 2. So this is like I is iterating. I is the index of the element in the list, and the ith element is at the location num consumed plus I mod buff size. Which from the picture, so this was num consumed. So starting from num consumed, we are laying out all the active cells. And then starting from num produced plus 1, we are laying out all the inactive cells which have NER ownership. So we are going from here to this point. So now we can look at, so num consumed all is just slightly different from num consumed. It's saying that if we are if we are in the consume function, then we may be missing the ownership of the first element. So then if we are in the consume function, then num consumed all is 1 plus num consumed, which just says that we have lost the ownership. The ownership of the head element is no longer in the list. If this in consume is 1, then num consumed all, we add 1 to num consumed, and which means that this array would start from 1 plus, and this current items would have one fewer item. So we are dropping elements. So it will have one fewer element. So this is just saying that num consumed all is just saying that if we are in the consume function, the ownership of the head cell is no longer in the invariant. So that whoever in consume, whenever we set in consume to true, this value becomes, we add 1 to this value, and we have ownership of one fewer cell in the invariant. Similarly for numProduce, it tracks, like if this Boolean is true, then we have ownership of one fewer cell in this predicate. And we have slightly stronger constraints. So previously in the slide, I showed that num consumed less than num produced in the proof. And that's what I wrote initially in the proof, but it turned out I need something stronger. It says that if we are in the consume function, then num consumed plus 1 should be less than num produced. Because we have already, at this point, we have already decided to consume one extra element. So we need a stronger constraint that num consumed plus 1 should be less than num produced. Similarly, in this case, if we have already decided, if we are in the produce and we have decided to produce, then this value becomes 1 plus num produced. So this is, it's hard to come up with the exact invariant in the first try. I didn't come up with it in the first try. I made some mistakes. This was just num consumed, and during the proof tells you, like, when you go to reestablish the invariant, you cannot, and then you have to come back and tweak the things and strengthen the things so that everything fits together. I don't expect you to understand fully, but any question that I could help with, help understand better, any question here? And so that P was here. So it says that we iterate over this list, and we have not just the ownership of the cell, but also if that cell has the value item, we also have P item in this array. So for every item present in the list, we also store P of that item in the list, so that when the producer produces, it deposits this P item in the invariant, and when the consumer comes along, it takes out this P item from the list. So in the inactive cells, we do not have P because yeah, those have been taken out. So for the inactive cells, we just say they have any value. We don't care about what that value, and we don't have P for the inactive cells. We only have P for the active cells. And one last thing is that just like physical locations, they had fractions. Even for logical locations, we have fractions. So we're saying that we put the half fraction of the in-produced location in the invariant, and the other half is owned by the producer. So just like before, this is like producer has the authoritative ownership of this in-produced location. So which means that the half is in the invariant, and the other half only producer has. So nobody else can change that value. They can read this value because the half ownership is in the invariant, so everybody can read this value. But to change that value, you need the other half that only the producer has. So only the producer can change in produce. And the other thing is also, one thing I didn't mention so far is we also have ghost locations to store the entire history of whatever has been produced so far. And we also store the none consumed in the list. So this is not essential, but it also makes our life easy. So what we are doing is like we could have just stored. So we want to say that the producer has exclusive authoritative ownership of the tail element. So the tail is num produced, mod buff size. So we could have just given the producer authoritative, like half ownership of that tail field, but the tail field is like not mathematically nice. Like it wraps around. In the logic, it's nicer to just have the actual value. So num produced location. Um, so num consumed location stores the actual value of num consumed. So there is no mod here. It stores, like it can store, even though the queue size, the buffer size is 8, it can store like 99 or something. So it stores the actual value of how many have been consumed. There is no mod here. So we also store these two like more logical values where we do not have to worry about implementation details. We also store that in the logical locations. And then what we do is like, even for produced list location, we store half. So we store the entire history of whatever has been produced so far. We store the entire history in this location. And as usual, half is in the invariant, and the other half is with the producer. The producer has the other half of produced list location. So only the producer can change this list. And conversely, for the consumer has half ownership of in consumed location and the num consumed location. So only the consumer can change these two logical locations. And because that the value at the tail cell is completely constrained by num produced, indirectly the producer, let's say the consumer has indirect exclusive authoritative control over the head field. Only the consumer can change num consumed, because only the consumer can change this field, because the value that is stored there is a function of num consumed, and this num consumed can only be changed by the consumer because they have the other half. So far what we have is producer has authoritative ownership of these two locations, consumer has authoritative ownership of these two locations, and all the constraints are like are there in the invariant, and all the ownership of the cells, all the active and inactive cells, all of them are in the invariant, and depending on that Boolean, the number of active cells may be one more, and the counting works accordingly. So now we can see the spec of produce. So it says producer at the location this we have producer R, and because I'm the producer, like the producer knows has like the full control of what has been produced so far. So it says that what has been produced so far is exactly that value, and they also characterize they have the P, and the argument to produce is this value. It is an integer, and one precondition is this P of value. So we have to transfer this ownership from the producer to the consumer. So we have to give up that P value at this time, and which the consumer would get back. So when the consumer returns in the post condition, the same P the consumer gets back. And the post condition for produce, it has a Boolean. So it says it can either succeed or fail. And if it succeeds, then the the produced list has one new item at the end. And if it fails, it just returns back the original resources. So it returns back this resource and this resource because it could not put it in the invariant. And the consume spec is dual. So we have some consumer R, and here the consumer has control over how many elements have been consumed so far. And so it returns by reference. So it has at the value location, it has some location, some memory location. At that location, initially, it can be any value. And if the consume succeeds, then that location must have some integer, and we get P of that value back. And if it fails, we don't, we just return the preconditions. Does the spec make sense? Okay, so we can look at the proof, just a few key steps in the proof. So this is the proof of the reduce function. The first thing it does is calls load. So as before, because it's an atomic operation, we get to open all the invariants. So that big invariant is now open, like that scene box is gone, and the entire contents of the invariant is available for use. So one crucial point was in the beginning when we start the proof, we must know that introduce is false. If introduce is already true, then we won't be able to take out the ownership of the tail cell. So it's crucial that at the beginning we must establish that introduce was false, and that's why we had in producer R we have this assertion saying that introduce is false. So and so which the precondition says that we are not in produce already. So in the invariant, as before, the invariant just says that there exists some Boolean in produce load head. There exists some Boolean. It could be true or false at this time. So we must show that this value is actually false, and as before, because we have this precondition that in produce lock is false, we can combine the two pieces. So this is the one piece of in produce location, and the other half is here. And once we combine those two, we get to assert that in produce load head is actually false. And so that helps us in the proof to know that the ownership of the tail location is actually there in the invariant, so we will be able to take it out. So now that in produce location, we combined both the half pieces, and they became one, and we just have false. So now we know that the ownership of the cell is there. So at this point, we know what the head is and the tail. So at this point, we can decide whether the queue is full or not. So we can make cases whether. So when we open the invariant, we get the current value of produce L. And so we know that value, we know the number consumed. So now at this point, we can decide whether the queue is full or not. So we make cases whether the queue is full or not. If the queue is full, um, there's nothing more interesting going on. So if the queue is full, we just return the original state. If the queue is not full, then something interesting happens. So if the queue is not full, then we know that we will succeed. So at this point, what we do, just like the new thing here is like, as before, we have opened the invariant, so we need to close the invariant. This modality tells me that we have to now close the invariant before producing. But the new thing we can do is that before closing the invariant, we get to change the values of logical location. So at this point, after just before closing the invariant after head.load, what we can do is update this ghost location. Introduce, we have full ownership in our wallet, and so we can change this location. So the rules are same as before. Like if you have full ownership of something, you can change it. Just like physical locations, even for logical locations, if you have full ownership of a logical location, you can change it. So at this point, we are just finishing up with the first atomic operation, which is the load. And at this point, just before closing the invariant, we are saying update this location to true. So now we are in introduce. And now that location has been updated to true. And then we close the invariant. So it's important we update that location before, that logical location before we close the invariant. And as a result, what would happen is when we close the invariant, the ownership of the atomics, they all, everything that is that the invariant holds. We have to reestablish the invariant. So all the atomics went back. The new thing is that we got ownership of the tail field. So produced length of produced L mod 256. So the buff size here is 256. And so we got this ownership of this field out. Even after we closed the invariant, we got to keep this ownership because the ownership of this field, this cell does not, because we set this to true, because we set in produce to true, this ownership is no longer needed in the invariant. The definition, the conditional says that this cell is no longer needed in the invariant, so we get to keep it even after closing the invariant. We have lost ownership of all the atomic cells and all that, but we get to keep the ownership of the cell, and this is crucial because we will write to this cell at this point. And so the precondition of that write is now there. And we also have now we have half ownership that in produce is true. So the other half went back to the invariant. It was existentially quantified. So the automation will automatically choose the existential quantification to true. And the other half we get to keep. So we know that we are in produce. So next time, because there are three atomic operations here, head and tail and then store. And all these atomic operations open the invariant. So next time we open the invariant, even though in the invariant, the value of in produce is existentially quantified, we can use this to say that no, that value is actually true. So now we do the step, which is fine. So we store the value in the cell. And now we are at this point where we are doing this. This is the next crucial step. Where at tail.store, we have to put back the ownership of the new cell in the invariant. So the definition should be that the invariant should absorb the ownership of this cell. So at this point, what we have is just before closing the invariant for this tail.store. So just before that, the physical location has been updated. So now if you can see the context, this is our wallet. In our wallet, at tail, we have length of produced L mod 256 plus 1 mod 256. So the C++ computation has happened. So next tail was tail plus 1 mod 256, and that's what we're storing here. So the C++ atomic location has been updated. Already, we are about to close the invariant for this store. Then the only thing we have to do is, before closing is now we have to update the logical locations. So in produce now we have to set it back to false. We are done with the produce and we have a new tail, and the ownership of that new tail must be in the invariant so that a consumer can use it. So we set that logical location back to false here. And we set the logical location tracking the entire produce history. We append the new value to that location tracking the entire produce history. And then we close the invariants. And then everything would match up and the proof goes through. Okay. And there are some modular arithmetic reasoning steps, lemmas like this. That there was otherwise the proof is just like once you get the invariant right, the proof goes easy. And but if the invariant is not right, then things won't match up. When you close the invariant, things won't match up. You require something else, and then what is there in your wallet, and there is some array manipulation going on in this proof, but otherwise there's no other complexity. There's any questions? Okay, so now I want to go to the next topic, which is monoids and ghost locations. I want to motivate why we need them. Um, so we already talked about logical locations, and in the literature they are called ghost locations. So I may be like using both words. So just sorry about that. Sometimes I say ghost location, sometimes I say logical location. They are both the same thing. So they are just like physical locations. They are logical locations where just to do the logical reasoning, we can store some locations. We can store some any cock value in those locations, and they typically denote like at what point are you in the proof, like how much progress you have made towards that operation. So, like here it was introduced true versus false. In more complex proofs, the operation takes many more steps, so it may have like 3 or 4 possible values, how much progress you have made. So that's one use of logical location. So the other use is so, so one is to track how much progress we have made towards the some operation, and something that's not like if you do if and some especially if you cannot tie it down to an actual C++ variable, then we often want to create a logical location for that. And then another use is expose the higher level state to the client. So that we also saw that use here. Like even though the tail field stores like the counter mod 8, we store the unmodded full value here, the full history, so that the client doesn't have to reason about the mod stuff. So we can use logical locations to expose a higher level state uh, for the clients of the specs. And then we also use logical locations to enforce complex protocols. And that's the thing we haven't seen so far. And that's the thing we want to see next. So to motivate that, so there is one weakness in this spec. If you saw the consume spec before, they just say that you can just return false. So this says that there is an arbitrary return value. It can be true or false. If it's let's say yeah, if it's true, then you get something out. If it's false, you get nothing out. You get back whatever you put in unchanged, and you don't get that P of consume V. So it can fail. So we are under constraining it. We are not constraining when it can fail. So this spec would work fine completely for a function that does nothing and always returns false. So if the consume body was just return false, this proof that even that function would satisfy the spec, and the proof would go through because it doesn't constrain the return at all. Just says that return can be false. So this is saying that there exists a return, there is a boolean, and the return value is v bool of red, and depending on that, so we are not constraining when you cannot, the success case. We are not preventing it from failing. This spec is not is like under constraining when it cannot fail. And we'll try to constrain it a little bit. We cannot fully constrain it because we have a consumer and we also have a producer, and the producer, whether it fails or not, depends on what the producer is doing. So it's hard to constrain it fully, but we can do better than this, and that's what we'll see next. So but we do not have anything so far. From what we have seen, we do not have anything that we can use to constrain. So we can try a few things, but and they don't work, and then we'll see a new mechanism, new flexibility that makes it work. So we can try. So one thing we want to do is like, so we want to say something like, if num produced current is the current number of produced items, we want to say something like if num consumed is less than num produced current, then return must be true. Then we must succeed. We want to say something like this. Make sense? If num consumed is num produced less than num consumed current, then it means that there is an unconsumed element in the queue, and that can be taken out. We want to say something like it. But this, we cannot say this, and for good reason. Because the producer, this num produced current is something that is not stable. Like the producer can be racing. We know that the producer is racing with us, so the producer can be changing it. So we cannot, in the spec, we cannot get access to the current value of num produce because the producer can be changing it while we are running. So we cannot just say that, and that's for good reason. But we can say something different. Or we can say, and I'll show you how to say it the right way, is that if we can have a preconditioning, then there exists a lower bound on num produced. So if the caller can show that there is a lower bound on how many have been produced, then we can say that if num consumed is less than the lower bound on number of produced, then we must succeed, then return must be true. Why? Because the producer can only produce more. So num produced only increases. So num produced was the entire history. So the producer, the only thing the producer can do is produce another element, which would only increment this value. And if num consumed was already less than the lower bound, that means that there was already some element and there can only be more elements in the queue. So num consumed, so consume cannot fail. So we want to say something, assert a lower bound on num produced somehow. Make sense? And so far, we do not have any mechanism to say that. So we could say that there exists, so num produced lower bound, we can say that there exists some produced L such that produced list location has produced L and num produced is less than num produced L length of, so we can existentially quantify over produced L. You may think that this works, but this doesn't work. The reason is that even though this is existentially quantified, this assertion says that the produced list always has that particular value. It can be anything, but it has that value throughout the entire call of consume. This assertion lets the caller lets the implementation of consumer assume that the produced list is produced L throughout the call, even though it can be an arbitrarily existentially quantified value. It lets it assume that it's the same throughout the call. So this doesn't quite work. So that's why I'll show you a mechanism where we can write these kind of assertions. And so this doesn't work. And also the other point is like we say 1/4. So to say that some value of memory has some value, some memory location, some physical memory location or logical memory location has some value, you must need some ownership of that. To talk about the value at a location, we need to have some ownership of that. And we do not have any ownership left. Half was in the invariant and the other half is with the producer. So there is nothing left for the consumer to even talk about that value. And this is a problem that will get fixed with the new primitive. Okay, so those things are so in the we have demo 3 proof 2.v which has different specs which makes us assert those things. So if you look at this notation, this says own AR where and so if you check the type of own, it says that there are these implicit arguments, and then there is this argument which is the ID of the logical location, and this is the value that is stored. And what the type of A is a CMRA. It's called a camera. It's the full form is commutative monoid resource algebra. And this is a very powerful mechanism. I think this may be the main innovation in the iris separation logic. This is maybe the main new innovation. Yeah, at least in my opinion. So what this says that at ghost locations, at logical locations, you can store any, you can store, you can come up with your own type of ownership. So what this allows you is you can define your own notion of ownership, and store that in the logical location. So you can come up with your own notion of ownership. So all you have to do is define a commutative monoid. So just some details on what a commutative monoid is. So I'll go into the Iris paper. The title is in the COG file. So we can come up with an arbitrary monoid, and so a monoid has carrier elements. So the carrier elements of a monad monoid is you can think of them as pieces of ownership. So elements of the monoid, you can think of them as pieces of the ownership. And then there is a dot binary operator. You can think of them as what does it mean to combine two pieces of ownership, right? And you can come up with your own notion of ownership. And you have this bottom element, which defines like that this element is invalid. So you can, and uh, and then you have this empty element, which means that you have no ownership. So to define a monad, we have to come up with, define a monoid, we have to come up with these items. We have to come up with a carrier type, which defines like the pieces of ownership, and which pieces are valid, and this binary operator, which says like when can we combine two pieces of ownership, two disjoint pieces of ownership, and that t and that whatever we come up with, T star U becomes T star star U, the star in the separation logic we saw on the last two lectures. So you have a customizable value of meaning of star. So you can come up with your own notion of star for the monoid you choose. And we'll choose a monoid, an appropriate monoid in this case, which lets us make those assumptions. Even without ownership, we can make the kind of assertions that say that the produced list, no matter what it is, it must be a suffix of some value. We can make these kind of assertions even without ownership using this very general mechanism. And just to give you a simple example, what we have already seen so far, like logical QX, so this is what we just saw in the proof. That is just a camera they have defined in the logic. So we said that at the logical location L, we have the value X with ownership Q. So you can think of the monoid element as a tuple, like as a pair of QX. So at the logical location L, we have the tuple QX. Q is the ownership, the fraction of ownership, and X is the value. And composition, like the dot operator, combining the ownership is defined as usual. We already did this many times. We could combine the two fractions as long as the fractions are less than equals 1. And we can only combine two pieces if they agree on their value. So we already saw these properties before. And then what falls out is using a monoid definition is.
A quick question. So when could the fractions ever be more than one together?
If they are more than one together, then it means that you have a false assumption in your context. So you made some assumptions that were not consistent.
Okay, thanks.
So actually, you can actually prove false from that as soon as you have more than one. And then, so this is the key thing. From this monoid, what falls out automatically is the definition of when can you update the ownership at a logical location from A to B. And that definition says that you can only do that update if for all frame F. So if for all frame ownership F such that F is combinable with A, then B must also be combinable with F. So this is a very generic definition that falls out. Like when can you update a logical location from A to B? To give you an example, so just this definition implies that for this particular fractional monoid, you can only update it when you have the full fraction. You cannot update it when you have a partial fraction. Why? Because let's say you have only this fraction 0.5 and the value is x. You update it to some value y that's not equal to x. Then we can pick the frame as 0.5 comma x. Right, so that's a valid frame because these two can be combined. These two can be combined, but these two cannot be combined. Right, so that's why you cannot update 0.5x to 0.5y because it refutes this requirement, this definition of when we can update a logical location. We can intuitively it says that if some other thread can be whatever other threads are owning, they must be consistent with my update. The assumptions of other threads cannot be invalidated by my update. Intuitively, that's what this is saying. And last week, like Kushal was asking, like, why don't we see the place where we reason about other threads, what other threads are doing? And that's because, like, in the definition of when they set up this fractional ownership, they've already done this reasoning once and for all for us. For this particular monoid, they have already done the reasoning that you can only update a logical location when you have full ownership. And if you have a fractional ownership, then you can depend on that being true. So when they set up this fractional ownership, this fractional monoid, they already did that ownership. They already did that reasoning that we can use. So here what a more general thing we'll see is STS with tokens. So this is a particular monoid construction that they have already done, and it's quite useful. So I'll show you a variant of this particular construction in the paper. This variant, in some applications, this variant turns out to be much easier to use. So that's what I'll describe, a particular monoid construction that will help us make the state the precondition that we wanted to state. So what are state transition systems? So the idea is you can define a state transition system which says that your concurrent library can have some state, and then you can define a step relation saying in what are the possible ways in which the concurrent library can go from one state to the next state. What are the possible allowed next states? You can specify that. And once you do that, you can make the kind of assertion saying that the produced list can only go up. So we have to make that formal by specifying your concurrent library as a state transition system. And one addition here is that from the typical state transition systems is that in this state transition system, you also have tokens. There you can have some tokens that guard certain transitions. So the state transition now is a ternary relation, and I'll show you the example. So this is the state transition system for the SPSC queue. So the state is the number of the items that have been produced so far, the entire history, and this is the number of items that have been consumed so far. There is no mod here. Like, this is the complete unbounded number and in cock. So that's the state. And then we have the step relation. We have two tokens. One is the producer token and the consumer token. And then we have the step relation, which has two kinds of steps. One is the produce step. This says that the produce step must require the producer token. So it says that only the thread who has this producer token can do this step. And the step goes from one state to the new state where we have appended some new item to the previous state, and the num consumed part remains the same. And conversely, there is a consume step where you must have the consumer token, and you go from previous to 1 plus num consumed previous, and the produced part remains the same. Makes sense? Any question? Okay, so now we can we can use the state transition system in our specifications. So previously we had two locations, ghost locations. One where we stored the entire produced list, and when we and the other one where we stored the number of consumed. Now we can just have one ghost location that stores both of those things. And so here is an example assertion. It says that at ghost location, one final step, I skipped something. So I said that the monoid has some carriers. So what are the carriers of this STS monad? So there you can make two kind of assertion. We can say that the state is, you can make an authoritative assertion saying that the state is this particular value and you have this ownership of these tokens. Or you can say that you can make a fragmented assertion saying that the state is one of these sets. So now this is a set of states. You do not know the exact state, but you can still assert that the state is one in this set. And you can also assert ownership of these tokens. So here is an example. Says the state is currently S exactly, and this says that the state is any value in this set. So here is an example assertion. This says that at the ghost location, we have the exact state where the produced history is 4 and the num consumed is 0. So nothing has been consumed so far, and we own no tokens. So now comes the main difference. So previously there was this thing called logical update, which says that you can go from for a regular logical R, you can go from one value to a completely arbitrary value v prime. If you have one ownership, you can update it in any way you want. That was the previous logical R we saw. You had complete freedom on how you can update the new value. Here, this is different. Here it says that if you have the authoritative, you can update it to some other value, some new state, but that new state can only be one where allowed by the step relation using the tokens that you own. So now you cannot, so this formally encodes the assertion that you can only step in the ways that are satisfied by the step relation. So now because we have made that assumption formal, we can reap the benefits. We can say that the produced list can only go up, even if we have no ownership. So just to do an example, we can do this update. We can, once we have the authoritative and we have the producer token, we can update it from the empty list to 9. That's allowed by the produce step. And the producer requires the producer token, which we already have. So we can do this update. We cannot do this update where we go from, we cannot do this update where if you only have the consumer token. If we have the consumer token, we cannot do this step because this step requires the producer token. So the consumer cannot do this update. Also, we cannot never do the update, no matter even if we have all the tokens. This top says like complete set. So even if you have all the states, all the tokens, you cannot still go from the state where the produced history is 9 and make it empty. So this is like formally encoding the ways in which the states can step, and the advantage of that is now we can derive these lemmas, saying that if we know that the produced history is 9.8, then if from this auth that the produced history is 9.8, we can derive, we get back this auth assertion, but we can also get a free fact saying that we can get a frag assertion saying that we are in a state where the produced history is a suffix of 9.8 and num consumed is greater than equals 1. So we get this assertion for free. So that's the key advantage here. Here and we get this stat that there is a condition. We don't get it for, we cannot cook up an arbitrary set of states. There is a condition. To get this flag, we must prove that the set of states is closed, and that's a very important concept. This lemma only holds when this set is closed. So we can see what closed means. So closed says that so one way to understand closed is that this set of states is closed under my tokens if for every other token that is not in my tokens, if for any S1 in S, some other thread can step from S1 to S2 using other token. So I don't own that token, which means that some other thread can own that token. And if that other token allows any thread to go from S1 to S2, and S1 is in S, then S2 also must be in S. So this is the key part so this is where we respect other threads' ownership. If some other threads have some ownership of some tokens that allow them to take some transitions, we can only assert a fragmented ownership of a set that is closed under those transitions. Makes sense. So if you look at the proof, so here Coq is asking me to prove that this set is closed, and this set is closed. This set is closed because the producer can only produce something. So this list will only become, you can only add something to the end of this list. So it will still be a prefix of that. And you can only increase num consumed. So that again would only increase. So this is a closed set, which we can prove. And once you have proved closed, then we get for free this kind of assumption.
Sorry, can you very quickly again explain the statement, the frag statement? Like what exactly did we prove here out of thin air?
Oh, out of thin air, yeah. So out of thin air is saying because we do not have we started from this, and then on the right hand side of the entailment we have this thing, and we get this fact for free, even without ownership, without any ownership. That is something we could not have done before. Previously, just before I said that to assert something about a state, anything about a state, we must have some ownership. And here, even without having any ownership, we do not own any tokens, and yet we can assert this fragmented ownership, that the set of states will always be in this set.
And the set of states says that, okay, the produced at least contain 2 items, and that's because you never remove items from them.
Yeah.
Okay.
Yeah. Because yeah.
Okay, and the number of consumed. Okay, so you're essentially constraining the state space that you're moving in.
Yeah, because the authoritative we have explicitly enforced that state transition system by using this camera.
Right.
And because for any update, because the update rule only allows you to update, take the steps that are allowed by the state transition system, because there was this lemma. Yeah, only if you can step from S to SF using your tokens, only then you can update from S to SF. That's why we can reap these benefits.
Okay, but this you have to kind of manually specify, or is this like this this frag statement? It's not a complete characterization of the transition relation, right? It's just like you just specify some facts like that you can extract from the transition system.
Yeah. The complete transition, the complete specification of the state transition system is here. Like we
Right.
define this state, so that's the complete specification, and now we can use that in specification. So now we can do the thing that we were not able to do that before. So now we have a new spec where we are able to do it. So that's
Okay.
but just before I get into it, just it's always good to see some negatives of things. So negative examples, not just positive examples. So we can say that this state, we can prove that this state is not stable under the consumer token. Why? Because the producer can always produce something and change this list. So the produced list being exactly equal to nil is not a stable assertion, and we can prove it. It's not a closed set, and we can prove it. Okay, that's it. And now we can look at the new invariant. The new invariant where here now we at the ghost location we store the authoritative and some state, and there are no tokens in the invariant. And the producer token lives with the producer. So what the producer has is the producer token, and because they have the producer's token, they can exactly characterize what is the produced list. So this is stable under the producer token. So as before, the producer can authoritatively specify what is the produced list. No change there, and just so this part is like almost equivalent in power. The only difference is previously the producer could have updated the produced list any way we want. In the previous spec, we could have a new produce function, produce2, that actually removed items from the list. Now that's not possible because we have enforced this state transition system. The producer has authoritative ownership, but the producer can only increase that list. The producer has to obey the state transition system. That's the only change. Otherwise, the producer still has authoritative ownership of the produced list. And so now we can do what we were not able to do before. So now we can say that there exists some lower bound, and we have a frag saying that the length of produced is greater than the lower bound, even though we do not own any tokens. We can still say that, make that assertion, and then we can use that to constrain when we can return true or false. So if the num consumed is less than the lower bound, then we must return true. So now we can do that and prove this spec. Okay. I wanted to show one last thing. I wanted to show like how this changes when we have multiple producer, just to set like the expectations. So I don't know, can we do like, we have 3 minutes left. Can we do like more 10, 15 minutes? Okay.
If I may interrupt this, another question I have, like you're going in the direction of multi-producer, multi-consumer, but I'm actually also interested in the same single producer, single consumer, but then a very different implementation. So now, what would be common and what would be different? That would be interesting. Anyway, I don't want to derail your like, but so you can have like the algorithm that we saw today. That's one algorithm. Another algorithm is actually the producer never looks at the head and the consumer. It's just like it's all like the consumer nullifies. It's like you have the concept of a null value.
I
that
see.
Actually, you only inspect the cell. And so that's another algorithm. So
Yeah.
you can see how very different, and it would be interesting to see like the spec where the commonalities and where the differences.
Yeah,
Because
yeah,
the
we
spec
should.
should be, again, from the outside.
It should be identical.
The same.
Yeah, then I think even in the proof, like the spec would look the same, and the definition of the invariant would change.
Right.
But these specs would just look exactly the same. I'm guessing, but I can look. I will look at your code.
It's just like I'm saying it's a different direction, but yeah, I'll let you continue with it.
Yeah, I think that's interesting. I'll chat and we'll take a look at it and see whether the specs are the same. Okay, so now what we have is the, if suppose there are multiple producers, then so what would the specs, how would the spec change if we have multiple producers? So the producer can now no longer say that the produced list is exactly some value. And the producer cannot even have the producer token because there are many producers. So there is no one producer that can own the token. So if we follow the previous approach, we have to put the ownership, we have to put all the tokens in the invariant. And that's like just a specific of this, of this particular design. But the main thing is that producer can no longer authoritatively say that the produced list is a particular value. The producer can now is just as helpless as the consumer now. Even both the producers and the consumers cannot say like what is the value of producer. So now they don't have the token, and the token is in the invariant, and even the producer can only say that the value is a suffix of something. But what they can say is that if it was a suffix, if it was a suffix of something in the post condition, if it succeeded, then the new suffix is like the previous suffix plus some new items that may have been added by other producers in meanwhile, and then the value that we pushed. So now the only thing that it can say is that the new produced fragment is that. Again, the producer has no tokens. This is something like saying that in the blockchain, we submitted a transaction, it's just saying that your transaction got added to the blockchain. And meanwhile, while these are the transactions of other producers, and your transaction got added. This is morely what the spec is saying. I have not proved this particular spec, but I believe it's correct and provable. And so this spec is okay. Like if really like if the client is really completely racing and using this class in a completely racy manner, and the client is not following any additional discipline, then this spec is the best we can hope for. So this is one thing to write concurrent specs, is to set the expectations. Like because of concurrency, we have to be mindful of what other threads are doing and not write preconditions that they can be violated. A pre-post condition. So on that vein, but yeah, if there is maximal racing, like the client is calling produce concurrently maximally and no other disciplines following, this is the best we can hope for. The problem is that if we write this spec, even if a particular client uses it in a sequential manner, they can still not, they still cannot get it. Let's say that there's a client which constructs this multiple producer, multiple consumer queue and adds and calls a push. Intuitively, we know that it must succeed because it was empty and then we added an element and there is no other thread racing. The client still gets only this precondition, and they cannot still prove that the produce must have succeeded. So that's a flaw, that's the drawback in this kind of specs. And so I'll show you a different kind of spec, which is more strong, and it lets the client choose whatever way. If the client chooses, the advantage of the new spec style I will show is that if the client chooses to use this library in a more disciplined manner, like if it uses only sequentially, then they can recover the strength of the usual sequential spec and not lose anything. So it's like a very strong spec. Like it's kind of the maximally strong spec that we can write. And it looks very different, and it looks very different and somewhat unintuitive. So that's what I want to show you last to end this lecture. And so, and it's very common if we write, whenever you're writing specs of a very concurrent library, you would write those kind of specs. And the style is called logical atomicity. So when you have a multiple producer, multiple consumer queue, what you're actually proving, if you ask like a concurrent algorithm designer, they would probably tell you that what the correctness property they have in mind is logical atomicity, which means that like even though the operation itself may have many atomic operations, it's a long function, the effect is as if it was completely atomic. Like no other thread can see what happened in the middles, the inconsistent states that were there in the middle. No other thread can see that. That's more intuitively, that's what the spec we want. So let's look at that spec. So first we'll look at the completely sequential spec. So even if we have the multiple producer, multiple consumer queue, if we wanted to use it completely sequentially, we can give it the spec. As before, we are like storing the complete set. Now we are back to logical R. We don't use that STS stuff because the point of this spec is to let the client choose whatever protocol they want to pick, whatever discipline they want to pick. So we just store half of the complete logical state, which is this, in the invariant, and the other half. There is only one, in this spec, there is only one producer or consumer. So there is only one thread that is touching the producer. So they have the other half. So they know that nobody else is changing the queue. So we know that the initial state is S in the precondition, and the post condition is the produced final state of that initial state S. The produced final state is here. Like if it's full, then the same as the original state, and if not full, then we add the new item. So this is a sequential spec, where like only one thread can access the queue. Make sense? Now we can take this spec and make it a logically atomic spec. There is a very simple, very straightforward cookie cutter formula to do that. So whatever was the sequential precondition, so we write this thing called atomic. I will describe the meaning, but this is called an atomic commit. This is saying that the change is happening atomically, logically atomically. And so whatever was the precondition, we put that here in the first bracket. And whatever was the post condition, we put that in the second bracket. And we say COM-QS. I'll get in a minute what COM-QS is. And that Q goes in the post condition. So that's all about the state change. And then also like if it succeeded, then we give the p-value back. So if it didn't succeed, we get the p-value back. That's yeah. So morally, it's saying that the post condition is not, we don't get that as a post condition. We get some Q as a post condition. And this is saying that at some point, this function will logically atomically change the state from S to that value. And so what does this AC mean? So to understand this, it's important to understand like what is, so it's a very extensional spec. And so to understand this, it will help to understand what is the specific, what is special about physically atomic operations? in the reasoning, what is the special thing that physical atomic operations allow you to do? So I think we discussed this in the last lecture and this lecture. So does anybody remember, like, what is special about physical atomic operations? What do they let you do that other operations do not let you do? So physically atomic operations, they let you open the invariant. So they let, before a physically atomic operation, before a sequentially consistent physically atomic operation, you get to open an invariant. And after the atomic operation, you must close the invariant. So that's something that you can only do for physically atomic operations. And what this spec is saying that what this AC is saying that you can do the same thing while using this function. So you can treat this function as a exactly same way as you would have treated a physical atomic operation. It's saying that to establish this precondition, so what's different between that precondition, so that precondition and this precondition is that because it's in an AC, it says that you are allowed to open invariants before you need to show this. So now the client, if it's for a RACI client, can put this in an invariant so that multiple RACI clients can take just for an atomic step, like just for this logical atomic step, just before this logical atomic step, they can take this out of the invariant and satisfy this precondition. So the only difference with this AC is saying that you are allowed to open invariants before needing to establish this. And then it's saying that then assuming that the state has been updated to this, after closing all the invariants, let Q be whatever is left after closing the invariants. And that Q can depend on the initial state. So that Q can depend on what was the state when you opened the invariant. So this Q is saying that whatever you can prove was left over after you close the invariants, that is what you get to continue with in the post condition. So this is an extensional spec saying encoding like whatever reasoning power was allowed for physical atomic steps. This spec extensionally like allows you the same reasoning power for logical locations. And we'll see a use of this spec. So we'll see how all that mechanics play out. But this is a very general spec. And so this now I'll show you what we can do, what we could not do before. What we can actually do is we can derive the sequential spec from this spec. That's what we could not do before. So this spec allows you to use it in a concurrent way, in a sequential way. So I'll derive two specs from this. So I'll derive a sequential spec, and I'll also derive a concurrent spec where there are multiple threads, but they follow a protocol which guarantees that the push would never fail. So they establish a protocol which allows them each of them to assume and rely and guarantee that the push would never fail because they follow bounds. And then we'll be able to derive a spec where the push always succeeds, even in a concurrent case. So that's the last two bits for today. So this is the spec. So this I proved the spec almost. There are just some trivial holes that are easy. So this is where I'm deriving. So I'm saying that the concurrent spec, the logical atomic spec, implies the sequential spec. So we can also, in the logic, we can also prove that one spec implies another spec even without looking at the code. So in this proof, we would not look at the code. You just imply that this spec implies this spec. And how these proofs work is like, if you want to prove this implication, you get to assume the preconditions of this spec. And from that, we have to construct the preconditions of this spec. Then you get the post conditions of this spec in your wallet. And then you have to show that those imply the post conditions of this spec. So we have to do this dance. So we start. So now we have all the preconditions. And so this spec has a precondition, the AC precondition, right? So we got the precondition of this, and now Cork is asking me to prove the preconditions of this spec. One of those preconditions was this. And to prove the precondition of this spec, one of those preconditions was this AC. So now Cork is asking me to prove that AC. So the new thing is like we can open invariants, but we don't need to, because whatever it's asking me for, that the state is some logical RSS, that we already have sequentially, because it's a sequentially spec, it's not in an invariant. We already have it there. We already have it there. So we don't need to open the invariants. We call this thing, it doesn't really open any invariant. We don't need to. And then we can satisfy that atomic precondition, and then we close everything, because we didn't open any invariants, we get to proceed. And now this final state, because we did not have to put it back in the invariant, we get it back, and we take it back as a Q. So this becomes a part of Q, and that's why we get that back as a post condition. So we can derive from that logically atomic spec, we can derive even the sequential spec, and then I'll show you how to derive concurrent spec, maybe 5 more minutes. So here we'll see how to derive the concurrent spec. So here, I will use the library in a concurrent way. And I've designed like a somewhat contrived protocol where the pushes, there are 2 threads, T1 and T2, and they guarantee that their pushes and pops are well bracketed. So they can push. They can only push up to 127 times, at most 127 times. And after that, they must pop before doing a new push. Same for both threads. So the capacity was 255. And if there are 2 threads, they are both running concurrently. So they are both pushing on their own schedule. But if they both guarantee that their pushes are not, number of pushes are not greater than number of pops by 127, then we can guarantee that the push would never fail, because we always have enough space, even though both the threads are racing. And we can, I just given to example of 2, we can have like 10 threads, and they all can have like 12. Their pushes and pops can be balanced by up to 12. We can do the same thing, but just for example, I've set it up for 2 threads. So I've set this up. To set this up, we put this ownership of this the logical state. The other half we have. Previously in the sequential spec, we had it bare. Now we put that in an invariant. And then we have two counters, two logical locations, which count the number of unmatched push or unmatched produce. I keep confusing them. So unmatched produce, they keep track of how many produces are unmatched by each thread. So Boolean, there are 2 threads, and for each thread we have a logical location storing how many unmatched pushes there are. So this invariant says that at state location there is some state, and the constraint is that the length of produced minus num consumed should be equal to the unmatched counts of both threads. Right, that's the constraint. And the number of unmatched counts should be less than capacity by 2, always. So that guarantees that we would never run out of space in the queue, even though there is races. So now, the only thing we did change, that previously this was sequential ownership. Now we put this in an invariant, and we set up a protocol. This invariant describes the protocol that the client would follow. And now we can prove this spec, where it says that with TID is the thread, layer 2 thread, TID is the thread that is calling, and they must show the ownership of the unmatched produce counter, and then they must produce, the precondition is that the unmatched produce count should be strictly less than capacity by 2, so that we can add 1. And then the post condition is that the unmatched count of that thread, because no other thread is changing this unmatched count is local for that thread. So no other thread is changing it. So we have the authoritative ownership of this logical location. So now the final count is 1 plus the field. So now we can prove this derived spec on top of the logical atomic spec. So this time what's different is we actually have an invariant. This time we do not sequentially own this thing. We do not own it sequentially. We do not have private ownership. It's only in a box invariant that the other thread can also concurrently access. So now but because this is an AC, we get to open this invariant. So this is this scene. So this thing is in a box. So this ownership is in a box. So we have to unbox it. And because we are doing a logical atomic operation, we get to unbox it. So because it's a logical atomic operation, this AC, just before the AC, we get to open the invariant, and then we get full ownership of bare ownership of the produce count. The produce count, and then now we can, and we also get ownership of the state, the other half that the precondition needed, and then we can satisfy and update the counts of the thread and finish the proof. There are 2 cases, one for each thread, and they're the same. So just to wrap up, for for concurrent libraries which have a lot of races, it's hard to say like what is this, hard to constrain the state. A very popular way to write the specs is so-called is to write this so-called logical atomic state, logically atomic specs where we have a ghost location that stores the high-level state. And then we set up I didn't show that, we set up an invariant where we connect the ghost state, the logical state, to the actual C++ state. And then such that whatever operations you do on the concurrent library, the answer can be read back from the logical state. We don't need to look at the C++ state. So we have to choose a logical state which completely characterizes the C++ state at a high level. And then we can tie that either in a lock. So in this example, I put that put all the ownership in a lock. So where was that? So this implementation of MPSCQ was a locked implementation. So there is a lock so there are many ways to write this function, but the spec would be the same. So I just wrote the simplest way. I just grab a lock before all operations. So multiple threads can call produce at the same time, but only one would get in. But we can implement it in a more concurrent way. But the spec would remain the same. What would change is the invariant, like the rep predicate of the class. So currently, what I do is in the lock, I store all the ownerships and the ownership of the ghost location, the logical location that is storing the high level state. Then I connect the high level state to the C++ state, like here. Head is num produced. So num produced is so this S directly flows here. So we have connected the logical state to the physical state in a lock or an invariant, and then write the precondition in the first part of AC and the postcondition in the second part of AC. And that's typically is very general, and you can derive many different. If the client wants to choose it to set up their own custom protocol, they can set that and not lose anything. the more discipline they follow, the stronger post conditions they can get here. So for example, in this example, even though it's racy, we were able to show that the produce must succeed. The post condition says V bool is true. So because the protocol we set up in this invariant, we can prove that this produce would always return false. Always return true even if it's racy.